everybody. Thank you for coming to this webinar today. I'm really excited to introduce Élise Beaudin, who's a graduate student at Brown University, to present her talk, Impact of Extratropical SST on U.S. West Coast Precipitation.
Hi, thank you, Mara. Hi, everyone. So yeah, my name is Élise. I'm a PhD candidate at Brown. I'm working with my advisor, Manu Di Lorenzo, and I'm going to present today some of my work. It's called Impact of Extratropical SST on U.S. West Coast Precipitation. It's a long title, but every word of this title is actually important. We are exploring, rather than the tropical impact of SST on precipitation, which is often done, we're exploring the extratropical. But I'm going to go through a rather lengthy introduction of this topic. I want to explore with you the normal conditions of precipitation over the U.S. West Coast, as well as all the modes and dynamics that we know that impact the rainfall. So, as we know, California is one of the largest agriculture producer in the world and the largest producer in the U.S., and there's increased threats of flooding and droughts and heat waves, as well as forest fire. And so it's really important to improve predictability in order to improve water management and as well, water management. So this is the motivation behind this work, because we really want to try to understand how can we better manage water for agriculture and other services in this region. So first of all, I'm going to go through with you the normal conditions of precipitation in this region. The West Coast in the US is largely impacted by this large-scale atmospheric circulation. So we have, actually, I don't know if you can see my cursor.
We can.
Okay. So, oh, actually, yeah, I'm not sure. Am I pointing over the Pacific High right now?
You're pointing over the Aleutian Loch.
Oh, okay. So I'm not gonna use my cursor, but I'm not seeing the same.
Okay.
So anyway, so the winter conditions. So we have this large scale atmospheric pattern, which is largely controlled by the Aleutian Low and the Pacific High. And so this is here the precipitation in January on the West Coast. We have a lot of precipitation in this region here because of the location of the Pacific High, which allows for the tropical storm of the Pacific to come all the way down here. Sorry, you don't see my cursor, on the coast. As for the summer, we usually have drought conditions in the south of California because of the location of the Pacific High, which is, in this case, blocking these tropical storms. So a lot less rainfall. So the precipitation on the West Coast is highly influenced by the strength and the location of the Pacific High. So again, just to show you again the winter conditions here, this is just a nice video showing the liquid water content traveling throughout the Pacific Ocean and going raining over the West Coast here. And so yeah, in the winter we usually have really, really high precipitation. In the summer, so there are some interesting dynamics at play here. We usually have drought condition over Southern California because of the North Pacific High, which is deflecting those storms. But there's also this North American monsoon system, which is located, so there's a high pressure system located over the US, which is bringing moisture from the Gulf of Mexico over the southwest of the US. And I'm showing here on the top left panel, so this is usually where the moisture is being drawn towards the US. It's mostly over Mexico and a little bit over Arizona. But if you look at the small figure at the bottom, we might have some precipitation over Southern California, even in the summer, because of this North American monsoon. So it's important to take into account all these large-scale motions that are at play when trying to predict rainfall over this region. This is just some examples of weather pattern. I took some screenshots from weather channels I found on the internet, just so you can understand more or less, again, the actors that are at play for precipitation over this region. So really when we have the high pressure system, you can see how the jet stream position is really being deflected. This is really what's going to impact the concentration of rainfall over California, the West Coast, and how if it's more towards the coast or higher, those storms are really being deflected. So now we're trying to understand what are the large-scale patterns that will influence the location of these high and low system. First of all, we have the Pacific Ocean North American mode, the PNA, which is one of the most important low-frequency mode of variability in the Northern Hemisphere. And it is not exactly associated with the Aleutian Low or the Pacific High, but it extremely co-varies with the Aleutian Low. So it's extremely important for the location of landfall of the track of the storms in the Pacific. So this mode is a quadruple pattern located at 500 millibars height, and the positive mode is associated with moisture flux convergence extending to the north, and a negative mode is more southwesterlies, bringing warm and wet flow towards California. And the PNA is actually modulated by sea surface temperature in the tropics, for example. So ENSO is an important modulator of the PNA. There's this interesting paper by Hu et al. In 2021 that was exploring deeper these modes of variability of precipitation over California. And they found out that, so the first mode, you can see on the upper panel with its corresponding principal component time series on the right, had a positive correlation with the Central Pacific sea surface temperature, but as well as the Indian Ocean sea surface temperature. So it really shows how remote teleconnection of the sea surface temperature in the world, so Central Pacific and Indian in this case, really plays a role in the local regional weather pattern of precipitation over California. The second mode of variability in this case was a dipole of precipitation associated with a dipole in vorticity at lower level in the atmosphere. So now you're getting a clear idea of what is controlling. There's a lot of large-scale atmospheric circulation that are important for these regional patterns in precipitation. And of course, we're not going to forget the most important of all, perhaps, is ENSO, so El Niño Southern Oscillation, hugely impact the weather patterns in this region and the whole world. So ENSO, as you all know, is the first mode of SST variability in the tropical Pacific, and is associated with, so excites Rossby waves that will then alter the Pacific High and the Aleutian Low in the Northeast Pacific, which will have a really huge impact on precipitation, landfall location, and intensity as well. But this is also really interesting because, so let's go through this figure. The top panel on the left here, I'm showing the pressure departure for both, so El Niño and La Niña, but two different cases. So El Niño in 1998, and which was associated with very heavily rainfall, and La Niña in 1989, which was associated with a drought over the US West Coast. And you can see here on the right, so the top panel on the right is the ENSO index, And on the bottom, it's not exactly the same time series, but it's the index overlaid with the precipitation intensity. And if you look closely, actually, you can see that usually El Niño, so the red, when it's positive, is associated with very strong precipitation, and usually La Niña is associated with drought conditions. However, in 2015, there was a very strong El Niño pattern, but it was also associated with drought conditions in California. So this is really not what was expected. So NOAA had predicted 60% above average winter precipitation in Southern California, with equal chance of normal precipitation in the north. But as you can see here, so let's look down at this panel here. Those are strong years of strong El Niño with their corresponding precipitation anomalies. And usually we have a strong higher precipitation on the West Coast. However, in 2015, 2016, there was extreme drought condition in California. So they concluded that most of the variations in that daily weather was mostly attributable to atmospheric internal variability, which just shows that we cannot solely use large-scale modes and atmospheric large-scale dynamics to try to predict the weather patterns in this region. So we have to look at different time scales and spatial scales as well. And lastly, you've probably all heard of the blob in 2013, 2014. So this was a marine heat wave, very long, prolonged period of hotter than normal SST, about 4 standard deviation than normal, which was located, you can see here in the SST anomaly map, and which was co-located more or less with a sea level pressure anomaly. So this pressure anomaly persisted for many months, and this caused a deflection of the winter storms. So those storms were not able to reach California. This is partly why also there was drought conditions during that year. But in this very interesting study, they made this really beautiful diagram here showing the normal conditions over the Northeast Pacific versus the blob conditions. And they showed that the blob primarily resulted from weak wintertime cooling due to the reduced turbulent air-sea heat flux transfer from the ocean to the atmosphere, so mostly sensible flux and latent heat flux, as well as reduced horizontal advection of cold water in the upper ocean. So we have this huge, this really important high pressure anomaly that stuck there for several months, then slowed down the winds, and that had impacts on both horizontal advection as well as air-sea heat fluxes. Now, this is a good segue for my study here, impact of extratropical Northeast Pacific, SST, and US West Coast precipitation. Why we wanted to look at extratropical SST is mainly because, first of all, most of the studies are looking at tropical impacts because most of the signal really comes from there. And this study was also motivated by the fact that there's an increase in frequency and intensity of marine heat waves in the Northeast Pacific. As you can see on the left figure here, so this is just so sea surface temperature anomaly in the whole North Pacific. And there was a paper in 1988 written studying the heat wave that happened in that time. So this is what a heat wave used to look like in those days. And now when we talk about heat wave, this is what I'm showing on the lower panel. So it's becoming more and more important to study all the mechanisms that are coming into play for impact of rainfall over the US West Coast. And on the right panel, I'm showing here this 2013-2014 during the blob, the California drought conditions, which was a historical drought condition. You can see here the precipitation index in 2014 was the lowest ever recorded. So let's jump into this study. For the experiment, we used WRF, a purely atmospheric model, version 4.0. So we ran for 10 years, 2010, 2020, over the whole Northeast Pacific, so the region that is located in this box. Horizontal resolution of 1/4 of a degree, and 30 vertical levels from the surface to 50 hectopascal. First of all, we had to run a ensemble. We had 8 members, and the difference between each member was really the so we slightly varied the initial sea surface temperature conditions, and we picked as our ground truth the mean of this ensemble. Now, our experimental setup, so we had 2 experiments, the warm and the cold, to which we overlaid for the whole period of 10 years a sea surface temperature anomaly associated with the PDO pattern, although so the study was not to study the impact of the PDO on precipitation, but rather we picked the PDO shape because it's a shape that occurs often in the Northeast Pacific. We had to pick a shape. We went for this one. And we picked a maximum amplitude of plus and minus 2 degrees Celsius. So for each of these experiments, so for the warm experiment, we have the normal SST conditions plus the PDO warm, a positive phase. And for the cold experiment, we had the SST conditions plus the PDO cold conditions. And then we ran for those 10 years. So first of all, model validation. Here I'm showing time series of precipitation values over 3 regions in California. We focus on California for reasons that I explained earlier, but also it will make sense more later to why we focus on California. But so here I'm showing those 3 time series of the data from our model with precipitation data from the CPC Unified Gauge-based analysis of daily precipitation. And it's just important to understand that precipitation is a prognostic variable, so it's an estimate using the model outputs. It's the sum of the convective and non-convective precipitation, which are both produced by parameterization in the model. So overall, there are some differences, but we deemed it good enough for continuing with our analysis. So now we explore the sensitivity of precipitation to the forced sea surface temperature anomaly. So on the right here, I'm showing again those sea surface temperature anomaly patterns that we use to run those experiments. And on the left, I'm showing time series of, again, these 3 locations: north coast of California, central coast of California, and the California desert. This is for the whole 10 years. And so the black line is the ensemble mean, and the gray shaded area is the ensemble spread. The red line is the warm experiment, and the blue line is the cold experiment. So what we can see from here is it seems like there is a consistent pattern of so inducing this warm anomaly along the coast seems to be resulting in an increase in precipitation, as for in the cold experiment, so having a colder spell along the coast seems to be resulting into lower precipitation rates over these 3 regions. But the California desert is actually more prominent, more interesting here. So we'll look at this more later. But however, I just need to mention, so we're not interested in individual events in this case, because this is an extremely, this is a very, this is not a real experiment. This is all model. So we instead look at the seasonal cycle over each of these regions. And here we can really see the differences. So those patterns are really highlighted, especially in March for the north coast and central coast. We really have significantly higher precipitation rate for the warm experiment and significantly lower precipitation rate for the colder experiment. And it's more prominent in March for the first region as for the California desert in September or late summer. We have extremely high increased precipitation rates for the warm experiment. So it seems like the summer monsoon has been exacerbated in the desert. So let's look at a couple of maps here. Those are climatology. So on the two upper panels are representing the warm and the cold experiment during the month of March, and the lower panels is during the month of September. The contour lines are the SST patterns, and the colors are the precipitation anomalies. So what we notice here is for the month of March, there's effectively much drier conditions. So when it's red, it means drier, blue means wetter. There's much drier conditions for the cold spell, and we have a kind of symmetric relationship, much wetter conditions for the marine heat wave conditions. What's interesting also is most of the anomalies seems to really be located over California. So this is why we focus over California for this study. And now for September or summer conditions, again, some symmetrical response, but in both cases, the anomalies are located more to the south, so over Baja California, Mexico, and slightly in the southern California, which is what we saw from those time series earlier. So the California desert is really the region impacted for summer month. So what are the mechanisms behind this? Why do we observe these changes? So to try to diagnose the mechanism behind these changes, we decompose our water vapor flux anomalies into 4 terms. So we have so I just want to mention, first of all, that those anomalies, the way we computed anomalies, were the output of the model of the experiments minus the ensemble mean, so minus our ground truth. So both anomalies for both cases are computed with respect to the same ensemble mean. So we divided into so Q and U. Q is the water vapor concentration, and U is the wind speed. The first term, Q prime, U bar, is the water vapor anomalies affected by the mean winds. Q bar, U prime is the wind anomalies acting on the mean water vapor. Q prime, U prime is eddy fluxes, and we have a residual term. And the residual term happened to be many magnitudes smaller than the rest, so I'm not going to show it to you here because it was almost 0, and it's irrelevant for the analysis. So for each of these months with the importance, so March to September, we looked at maps like this. Again, I'm not going to show for all of them, but it's just to show you how we did the analysis. We tried to look at each of the terms and then the sum of it. So if you look on the left here, this is a precipitation anomaly map with the wind anomaly map of 500 millibars. And on the right, we have, so the lower left is the sum of those terms, and the 3 other ones are each individual term. I just need to mention that the color bar scales are not the same. And I'm sorry if this is a little confusing, but we just really wanted to compare the shape of these to see, and the magnitude, to see which ones were really important. And if you can tell, so the Q bar U prime, so the wind anomalies acting on the mean water vapor flux, is really the dominant term. Yeah. So I think this is a better way to look at this here. So first of all, so for the March case, these panels here. So we're looking at precipitation anomaly again with the winds. In the center, we're looking at the corresponding sea level pressure anomalies, and on the right, we're looking only at that term that I said was important because we really try to understand what's the pattern that's bringing this extra moisture, basically. And yeah, so in both cases, the warm and this is the cold case here, the response is not exactly symmetric in amplitude, but we have an inflow of moisture vapor and then also outflow of moisture vapor for the cold case. And now for the summer, I'm zooming in more closer to Baja California because this was more the region of interest. Again, we have, so for the warm case, we have a higher precipitation anomaly, which is associated with also a high pressure anomaly over this specific region, but also a low pressure anomaly over the whole Northeast Pacific. And we have increased moisture flow over the south there. And similar, but inverse, we have moisture flow going away from the coast. But and in all these cases, the dominant term was actually the wind anomaly. So it's not the main factor contributing to this increase in rainfall is brought by an increase or a decrease in wind anomalies, bringing moisture to the coast or away from the coast. So yeah, so conclusion of this study, what we did is we ran a set of experiments with sustained warming or cooling over the Northeast Pacific using the PDO pattern. So as a prototype for marine heat waves, again, we're not looking at the impact of the PDO on the rainfall, but we just really had to pick a shape. So that's the one we went for. It really seemed like California was the most significantly impacted region. And all in all, I think the most important was that these changes in precipitation were brought through a dynamical adjustment from the by the large-scale alteration instead of a thermodynamical change. And of course, the caveat of this experiment is that this is an artificial experiment. We had sustained warming for 10 years, which is quite unrealistic, and hopefully that won't become the norm in the future. So it seems like from the study, we can see a SST feedback on the atmosphere, but brought from a dynamical adjustment. So there's this clearly an air-sea interaction here. So I hope that you learn something from this talk. There is clearly evidence of extratropical SST anomalies impact on regional precipitation variability through air-sea fluxes. The tropics are definitely not enough to predict precipitation patterns in the US West Coast. However, the challenge is really that the tropical SST and their impact has a much stronger signal. So we need to find ways to isolate the extratropical impacts. There's clearly an important role of remote forcing causing these precipitation anomalies over a wide range of timescales, but also a spatial scale. So mesoscale dynamics also play an important role in regional weather pattern. Of course, in my study, we really looked at a large-scale weather pattern, but we don't know if those changes in precipitation, we don't know if it's due to the whole large-scale SST that we superimpose, or what if we superimpose a smaller SST anomaly? Could we see also differences in patterns in precipitation? So it's really important to understand these mechanisms to help with predictability. And for future research, it would be interesting to explore different patterns of SST anomalies in size as well as in shape. And also maybe for future discussion, we could talk about what are the mechanisms we could explore, what kind of experimental setup would be interesting. And this really highlights the need and importance of having more observations across different scales, and in this case, especially smaller scales of physics and air-sea fluxes, because we know that the PNA, ENSO, large-scale marine heat waves seem to have impact on these regional weather pattern, but we still have a lot of gaps and issues predicting those precipitation, and I think that having smaller scale observations would help filling this gap. So I just want to thank first Mara, who brought me to this seminar, and my advisor, Manu Di Lorenzo, and these co-authors for this paper, Hyo Deseo, Art Miller, and Youngji Jo, and this research was funded by NSF. Thank you.
Thanks, Élise. That was a really fantastic talk. Really, really interesting.
Thank you.
So now we'll open it to any questions or discussion. And you can raise your hand or just unmute if you have a question. And maybe I'll start off the discussion and ask, so in observations, we will have superposition of tropical and extratropical signals. Do you have a sense of, maybe first, whether there are any interactions between tropical and extratropical SST impacts on precipitation?
Well, yes. Well, for example, the PNA. So because the tropical SST will impact the location and the strength of the PNA, which will be decisive of the location of the North Pacific High, which is also what is changing the location of the landfall of those storm tracks. Yeah. So I only know of one-way connection. I don't know if there's extratropical to tropical impact.
Yeah. Go ahead, Rick.
Hi, yeah, thank you. Élise, very nice talk. Can you comment on not the shape of the perturbation, but rather the time scale in which you might need the perturbation to exist in order to get the response that you're getting? In other words, say you were in a condition where the El Nino signal was developing still, so that the extratropical response may be developing as well. What sort of time scale do you think might be needed?
Well, we can look here at those time series here, for example, because the El Nino was really happening 2015, and in fact, sorry, we're not seeing the same screen, but if you look at the California desert time series, in fact, yeah, those precipitation are really through the roof. But in the early years, 2010, 2011, we already start seeing anomalies, actually. So no, that's a question. I don't know, but it seems like even early on there was already an impact. Although there's a spin-up time, which I think takes at least a few months, if not a year, for the atmospheric model. So, but yeah, already in 2012, 2013, we start seeing impacts of precipitation before the El Nino year.
Right. It's interesting because these intermediate scales are very difficult to predict, almost needing some sort of non-physical experiments in order to identify very odd interactions that might involve fully coupled simulations ultimately, but for which we
and
might
I
not.
actually have a colleague who is currently working on a coupled simulation. Chris Rankel at Hui is a postdoc of Beaudin, but he's exploring that more for specific events, but that'll be interesting to see, actually. Yeah.
Great, thanks.
You're welcome.
And I see Chris on the call, and so I don't want to
Chris
put you
is
on the
here.
spot, but if you do want to comment on that, that's also something we could open the floor for. But maybe next we transition if there are any other questions for Élise. Anish, go ahead.
Thanks, Mara. Thanks, Élise. That was a great talk and very nice work. I was wondering if you could comment on the non-stationarity in terms of climate itself, right? Like your results are really interesting. Thinking about as the climate is changing and especially the polar regions are changing rapidly, likely like the Aleutian region and sea ice there would change. How would those kind of global scale tropics to polar temperature gradients influence some of these results, right? They would influence the jet stream, they would influence also probably the SST
the location of
gradients,
the stream could be impacted by changes in the strength of the Aleutian low. I don't know. I mean, that's an interesting question. I don't think I can answer it on the spot like this, but if anyone else has an answer to this, maybe.
Yeah, I guess, there's more research to be done on that, right? Yeah, it's really interesting.
I think that, so as I said, obviously it's a very idealized experiment, but I think there's power to using those models actually that we can really try any scenario that we want. So it would be interesting to explore different coolings and time scale and also spatial scale, because in this case it's really large scale warming and cooling that we pick. But I would love to see what would be different if we change the location. And also we really picked so 2 degrees Celsius is quite strong, although as I said, the marine heat wave in 2013, the blob was about 4 standard deviation higher than normal, which to some locations was about 6 degrees Celsius. So it's not abnormal, but it's still very high. Yeah.
Right. And yeah, probably the PDO pattern could also be influenced, right, in the future.
Yeah.
If you're changing the basin. Thanks again, Élise.
Thank you, Anish.
I see Chris, go ahead.
Yeah, thanks, Élise. I hope you can hear me.
Yeah.
Just commenting on the question about the timescales, and because Élise brought it up, we are currently running a couple of experiments for an individual event, and where we remove and subtract or where we remove the marine heat wave from the ocean conditions, and our initial simulations show some response, but obviously not as strong as it is here the case, where Élise obviously has this warming pattern on top of the warming that's already in her control case. So, but even on like a synoptic time scale, we do see some impact of these warming patterns. So that I hope that answers Rick's questions.
Yeah. Thanks, Chris.
The other issue is the choice of region, where if you moved it into I mean, it's very interesting that you have the biggest signal in the early and late cold season, the shoulder seasons, because you also see the same interesting responses in the shoulder seasons in upstream in the storm track entrance areas. So related to Anish's question, I guess in some sense it'd be interesting to connect the two regions somehow in terms of their responses to their seasonal responses.
Yeah, are you talking about the changes in the pressure pattern, for example?
Yes, the fully coupled response.
Fully coupled. Yeah.
Yeah. It's just very curious that there's a bigger response. I've never seen this one, but bigger response in the shoulder seasons downstream, as well as an interesting upstream storm track entrance response as well in these seasons. It's just very curious.
I was going to ask if you have thoughts on how we can take lessons from this study and to think about mesoscale forcing of precipitation.
Well, I mean, so as I said, we don't know if it's the scale of the region, the warming that we picked that was decisive of these anomalies in precipitation, or was it the time scale, perhaps? So that we haven't explored either. But my thought is, for example, in the case of the El Niño in 2015, where even NOAA had predicted a 60% increase in precipitation over normal conditions, and it really did not happen, and they attributed that to internal variability. I'm thinking that maybe there's more to that. Maybe there was some mesoscale changes less obvious to us in the observations that were contributing to that as well.
Yeah, thank you. Are there any other questions for Elise? Yeah, go ahead, Tony.
Hi, Élise. A question about the boundary condition for the warp model. I may have missed what you described. It's some kind of climatological condition for the PDO, for the two phase of PDO, right? Doesn't have weather information from the side.
No, it's just a sea surface temperature.
Oh, I mean the atmospheric boundary condition in the warp model.
Era 5? Sorry.
Yeah.
Era 5?
That's composite, is it?
No, it's the
the actual time varying. Okay.
Yeah.
Okay, good. So that means the boundary will contain forcing from remote SST influence from the western part of the Pacific, say the Crucial mesoscale S interaction that perturb jet stream influence the atmospheric circulation, and that will come in from the side. I know it would be hard to isolate that part without additional experiment, but coming back to the figure where you showed the comparison of the model, PDO North, PDO, yeah, that one.
Two observations?
Yeah.
Or this one?
With observation. Yeah, the other one. Yeah. So does that mean that, let's see, I'm trying to assess how important the local SST in the Northeast Pacific is relative to the influence of, say, in the Crucial related SST that come to the boundary condition. So if the curves here are very close to each other, what does it say about the relative importance of the local SST versus Crucial SST?
So the importance of local forcing versus remote forcing.
Yeah.
Yeah, but there's also tropical forcing, I guess. I mean, I guess the question is
in there.
What's the contribution of individual local versus and remote forcing? But there's also, as this study showed, the precipitation over California was also correlated. The first model was correlated with the Indian Ocean SST, which induced Rossby wave train. So
Right. All of those come through the boundary condition of the
Yes.
atmospheric. Yeah, there's no way to separate it, I guess.
I mean,
So I guess
I think this is the way we can regress and maybe cancel some of the incoming winds, I guess.
Yeah. Right. So in other words, the finding of this study is pertinent to the local SST effect, but it does not say how important the remote SST effects are, right? Whether it's a tropical or it's the crucial. Is that a correct statement? Mm. Okay, good.
Yeah,
Thank
exactly. Yeah.
you. Okay, thank you.
Yolanda?
Sorry, yes. Just responding to Tony, we have done experiments like this for with WRF in the desert regions, the North American monsoon, and we've just filtered. You could just filter the incoming ERA5 information for synoptic variability. You know, you could, if you really wanted to take out any kind of wave trains, you could certainly look at seasonal variability at the boundaries or something like this. But I was wondering if you've looked at the studies in the North American monsoon region. There's a lot of literature there on looking at the influence of these low frequency modulators on the monsoon, because it was interesting to me that you had a large variability, the largest variability in the California desert region. And it does look like it's isolated to that low pressure or high pressure anomaly that's associated with your very strong SST forcing.
Yep.
But you are sort of in phase in September with the end of the monsoon in North America. But oddly, also you emphasize the Mexican monsoon there, which is typically earlier. So it's almost like you're prolonging it. Or, you know, there you've got a very dry anomaly in the opposite phase. But yeah, it'd be interesting to see how that might compare with that literature. I wondered if you had looked at that, even though I know you're focused on California.
No, I mean, we did look a little bit, but it's clearly, I mean, here this SST clearly induced this sea level pressure anomaly pattern here, which is what drove those winds here. Sorry, I'm not pointing exactly, but the wind anomalies were exacerbated, and it's probably what brought more of that moisture that maybe usually does not reach as far in the Southwest. And
yeah, it's hard to tell with the dark color. I can't see. I mean, obviously the wind anomalies are from the southwest here along the Baja Peninsula.
Yeah, you can kind of see on the right panel, the QU.
Oh yeah, at 850. Yeah. You're getting them right up the channel there. Yeah, I mean, that's more characteristic of earlier in the monsoon, but yeah, so, it's interesting.
I mean, this might be also an artifact of the shape of our long-term forcing, which also extended all the way down to Baja California. So it would be also interesting to explore what if we stopped at, I don't know, 30° north, you know, or yeah.
Okay, thank you.
Thank you.
John, do you want to go ahead?
Yeah, so again, great talk, Élise. And this is probably just a small question and probably something that I missed you mention. But since you said that this was just an atmosphere model and that you specified the sea surface temperature forcings, did you run any experiments, or do you have any idea of the scope of the change in evaporation flux?
Yeah, so this is actually what we are exploring through this We are trying to separate the impact of the increase in water vapor anomalies versus the increase in the wind anomalies, which is what is needed to bring that moisture over land or away, right?
Right.
And then in all the cases that we looked, the wind anomalies were really the dominant factor of this
So
mechanism. Yeah. So that's the interesting result, that we found out that the dynamical adjustment prevailed over a thermodynamical adjustment.
Okay, thank you.
You're welcome.
A moment for any other questions. And if not, let's give Élise another virtual round of applause for a fantastic talk.
Thank you. Thanks for having me.
Yeah, thank you again.
Thank you.